So we've seen parametric equations and we've also seen vectors in R3. So we're going to combine those ideas and describe vector-valued functions. So a vector-valued function and I'm going to abbreviate vector-valued function as VVF, is a function of the form as follows. So I'm going to write R with a little bar over it to help me remember this is actually a vector-valued function. The input to my vector-valued function is going to be some real number, and the output to my vector-valued function is a vector in R3. So a vector in R3 has three components. So I'm going to write this as f1 of t, some function of t in the first component, f2 of t, and f3 of t. So the output is a vector in R3. And you could think of a vector-valued function as parametric equations in 3 dimensions. So I have my x equation, that's my f1, I have my y equation, f2, and I have my z equation, f3. These are more than just parametric equations, however, because I have a vector. And with a vector, I could take dot products, I could take cross products. So I have more tools available than just parametric equations. Okay, let's see an example. How about the vector-valued function r of t, which is cosine t, sine t, and t. So I can plug in different values for t, and I can get out different vectors in R3. That's all there is to a vector-valued function. So r of 0, for example, I can plug in t equals 0, and I get the vector 1, 0, 0. I can plug in pi over 4. Then I get cosine pi over 4, which I think is square root of 2 over 2. Sine of pi over 4, square root of 2 over 2, and pi over 4. I can get another vector, let's just do one more, say, like pi over 2. That would be the vector 0, 1, pi over 2. Okay. I can imagine these vectors being drawn in R3. So let me draw this situation for this vector-valued function in R3. So I have 3 axes. I like to write the z-axis going straight up, the y-axis to the right, and the x-axis coming straight out. So when t is 0, I get the vector 1, 0, 0. I'm going to draw all of my vectors with starting point at the origin. So I'm going to just draw every vector I see here, starting point, origin. So the vector 1, 0, 0 is the vector that is coming straight in the x direction and is 1 unit long, a unit vector. So there's my value when t is 0. Then when t is pi over 4, I'm at this vector, which would be some amount in the x direction, the same amount in the y direction, and then up pi over 4, which is about 1. So, or a little less than 1, really. So this is here my vector pointing to this point in R3. That's when t is pi over 4. And then when I have pi over 2, I'm at the value 0, 1, pi over 2. So 0 in the x direction, 1 in the y direction, and pi over 2 in the z direction. Okay, so I get a bunch of vectors, and I could draw them all starting at the origin. I can plot more values of t, and if you do, you'll get more vectors that point at different values like this. And you can imagine a curve that passes through the points that my vectors are pointing to. So I can kind of sketch a curve here. I think it would go something like this. So here's my red curve. It's going to pass through the points on this curve. Now that's a horrible drawing of the curve, but this will actually describe a helix. Now I can't really draw these that well in R3, so in my next video I'm going to show you a computer-generated image of vector-valued functions, and I'll do this example. But what's happening here is the following. I can think of different vectors pointing to different points in R3, and then I can have a curve that goes through those points. Vector-valued functions are the key tool to understanding motion in 3 dimensions. So I'm going to use vector-valued functions to describe moving objects. And I'm going to use the dot product and the cross product and properties that I am familiar with from parametric equations to describe the motion of that object. Okay, see me in my next video where I actually show you a reasonable image depicting the situation here. Okay, I'll see you there.